Alright guys, so today we're going to talk about minima and maxima that are also going to be called extrema. So let's try to motivate that with a graph as we normally do. So let's say we have a graph that does kind of this, and then we're going to go and do this. Very interesting graph. I need two different points of interest, so we're going to look at that right there. Alright, so what I'm going to be interested in is finding where the function takes minima and maxima. So first we have to define what is going to be a maximum. So a function, or the function, let's say y equals f of x. So the function, and I went too high, and we go a little bit low. F attains a maximum at x equals c on an interval I, if and only if, let's write it with double F, or if and only if, f of c is going to be greater or equal than f of x for all x's in the interval. So what does that mean? Let me draw an interval for this one. This looks like it could be a maximum. Of course, the function keeps going higher, but I'm going to restrict myself to an interval here that I'm going to denote with I. So if this is my interval I, then this value, that would be my value c. So let me call it x equals c. Let's do a vertical line, I suppose, because I don't have room to write it. So let's say that that value x equals c is going to be possibly the point where the function takes its maximum. And how do we check? Well, we grab that value that we called f of c, and we compare it to every possible y value that the function takes, or that the function attains on the interval. And in this case, f of c is larger than f of x for all of those x's on that interval. So that seems like it's a maximum, but it's a maximum on this interval or any other interval that does not include, for example, a point here. Say this point is larger, or this value of y is larger than f of c. So if my interval includes that point, this f of c is no longer, or c is no longer a point where the function attains a maximum. So that kind of highlights an idea here that maxima and minima, or this what is called extrema, are going to be dependent on what interval we're considering. So let's call this now interval I1, and we would have, according to this definition, that f attains a maximum at x equals c for that interval I1. But now, for a minimum, you would just change the order of the inequality, and let's say that this is going to be my interval I2. And it seems like right around here, I obtain a minimum for that value right there. So what would be the characterization that we need for a minimum? We say that the function attains a minimum and I'm going to summarize everything, but the sentence is exactly the same. A minimum at x equals c on the interval I, or the function attains a minimum at the interval I at x equals c if and only if f of c in this case is less or equal than f of x for all x's on that interval. So that would be the minimum. Now, I chose this very particularly for a reason, because these are going to be called relative extrema here in a minute. But if we restrict ourselves again to I1, you can see that I have these endpoints for my interval, and it looks like right here my function is attaining a minimum for this interval I2. So with that in place, I can write what would be a minimum or a relative minimum and a relative maximum. So the function, I should have said, the function f attains a relative or has a relative minimum / maximum at x equals c if and only if there exists an interval I containing c such that x equals c is a minimum or maximum on that interval I. So what does it mean? Well, let's look at it here. So x equals to c is a relative maximum because I can find an interval. By the way, this interval I, we prefer it to be open. So let's put that there. An open interval. In this case, I drew a closed one. But this interval serves the purpose, or the open interval containing it, the smallest or largest open interval containing it. On that interval, this right here, this represents a maximum. Why do we want an open interval? Precisely to eliminate this possibility. Because this guy is not a relative minimum, maximum or minimum, it's just a minimum for this closed interval because it happens to be the endpoint of the interval. So, so this one we don't care about, so that's why we have the restriction for an open interval that I had not written, but that's what we need. So we have two different situations here. So what is a maximum on an interval? So the interval is given, and we look at the value, the largest value that is obtained, if it's obtained, or the minimum would be the least value on that interval. Now, the difference here with relative extrema and or relative minima and relative maxima is that we don't have an interval given. We say if we can find an interval, then that is going to be called a relative extreme. All right, so let's take a look at what will be the critical number. So remember my graph with the minima and maxima. I'm going to do something similar, but I'm going to be throwing in a little bit more. All right, so all of my interest points or types are going to be there. So we see that we have a relative maximum here. Let's call that C1. There's a relative minimum here, C2. There's an interesting point around here, which is neither a minimum nor a maximum, but the graph flattens out there, C3. And there's another point of interest right here, C4. So let's try to figure out what's happening at all these points. So what is the derivative at C1? Let's take a look at the tangent line to the graph at that point. Seems to be flat, right? Or horizontal, if you will. How about that one as well? This one, my graph is a little bit off, but let's say that there's a point where it flattens out. So it seems like the derivatives there are going to be turning to 0 at that point. But what about this one? It's a relative maximum, looks like it. It definitely looks like. But what is the derivative there? Well, you have a corner, so it could, if you compute the limit from the left, it would be that. If you compute the limit from the right, it would be that. And so they would give you a different value for the slopes. So it seems like at that point, the derivative is not defined. So those points are going to be called critical numbers. So a number or value x equals c is called a critical number of f. If and only if the derivative at c is equal to 0, or, see if I can fit that down there, I think I can, the derivative at c does not exist. So most people will remember the derivative being 0 because you will find that we're going to be doing that over and over and over, setting it equal to 0. But a lot of people then forget to check when the derivative is undefined. Let's do a couple examples where we compute the critical numbers to different functions. So first example, let's take a look at the function. I have x squared over 2 minus natural log of x to start. So let's try to find the critical numbers for this function. Remember that the domain for this function is going to be 0 to infinity, right? Because you cannot take 0 or any negative number, so you have to be strictly positive for the natural log to be defined. So that's going to be your domain, so you cannot even compute anything outside of that. So to compute critical numbers, we're going to take the derivative. And as you remember, this one will be 2 times x divided by 2 is just going to give me x, minus the derivative of the natural log, which is going to be 1 over x. And that then I can simplify by doing a common denominator right there. So multiply x times x gives me x squared minus 1. And so I have to find two things. Either 0 equal to the derivative, in which case that's going to be true when x squared minus 1 is equal to 0. The function, the derivative is 0 if and only if the numerator becomes 0. And this one is true whenever x minus 1, x plus 1 is equal to 0, from where I get two possible numbers, x equals to 1 or x equals to negative 1. Well, we do have a bit of a problem because negative 1 is not in the domain, so you do not list this guy because that is not a critical number to this function. So far we have 1. And this is where most people stop. And they forget and they say, wait, well, I'm done with critical numbers. And I say, no, wait a second. You still have to check for whenever the derivative is undefined. Now, looking at this function, the derivative does not exist whenever the denominator is equal to 0. However, x equals to 0 is not in the domain, so that is not a critical number either. So my only critical number is going to be x equals to 1. For f, for the function f. So you have a critical number right there. All right, so let's go ahead and compute the critical numbers for the following function. So x minus 2 and divided by x squared minus 5. Remember now here the domain, you already have to know that you have the domain is going to be from negative infinity to negative square root of 5 union, can I fit it there? Maybe. Let's try. Square root of 5, negative 5 to square root of 5 union square root of 5 to infinity. So you're eliminating the plus minus square root of 5 that make the denominator 0, and I couldn't fit that part, but I just want you to know, because whenever we compute our derivative, you will find that this points plus minus square root of 5 will come up again as points where the derivative would be undefined. but the function itself is undefined, so we don't care about those. So let's go ahead and take our derivative, and this is going to be a quotient, so we do a quotient rule. So derivative of the top is 1 times the bottom, x squared minus 5, minus the derivative of the bottom, 2x, times the top all over the bottom squared. And so we simplify, probably have enough room here. I get x squared minus 2x squared when you distribute. So you know what? Actually, let me write it all out. X squared minus 5 minus 2x squared plus 4x when you distribute. So it's a little bit more straightforward to see what we're going to obtain. And so here, once we simplify it, now we get x squared minus 2x squared, we get negative x squared, plus 4x minus 5, all over x squared minus 5 squared. And if you ask me, I always prefer to compute, to factor things that have a positive coefficient or leading coefficient. So I'm going to pull a negative out of there, and I'm going to factor it out. So x squared minus, because I have a plus, 4x, and then plus 5, because I had a minus, all over x squared minus 5 squared. So now we're in position to find our critical numbers. And to find our critical numbers, we set the derivative equal to 0. When does that happen? Well, that only happens when the numerator is 0, because if the denominator is 0, we get a point where the derivative is undefined. We'll deal with those later. So the only thing we have to set is the numerator equals to 0. All right, so to solve this one, you would end up with a quadratic equation. So negative b is going to be positive 4 plus minus square root of 4 squared, which is 16, minus 4ac, which is 4 times 5, all over 2a, which is that. And notice that we get a negative square root, so we get 2 plus minus 1/2 of the square root of, and here we get 16 minus 20, negative 4. So that gives us complex numbers. We're just looking for real roots, so that is not going to be useful to us. Here we get 2 plus minus I, so not really good for us. So there's no points, no critical numbers where the derivative is 0. So that's that. And now the other critical numbers we could obtain is when the denominator becomes 0, but that's going to give us plus minus square root of 5, which we already had included. So no critical numbers on the domain. Again, as I said, plus minus square root of 5 do make the derivative 0. However, those were excluded from the domain from the get-go. So we'll leave it at that for this one, and we will resume critical numbers and relative extrema next time.